Today we're going to spend a little bit of time on solving systems of conic sections. So what is a system? We've solved systems of equations before, and if you recall back from Algebra 1, a system of equations, we had a linear function and maybe another linear function, and they intersected. And we saw that they intersected at a point, and we called that one solution, and we were able to use things like graphing or elimination or substitution to be able to solve them. We also saw that these two functions possibly could have been parallel, which we had no solution. And we also saw that these two lines could have been the same line where we had an infinite number of solutions. And we'll also see these in our conic sections as solutions. So we could see one, we'll talk about maybe we could see more than one point of intersection. We could see no solution, or we could see an infinite number of solutions. We are going to ask you to solve these algebraically. I know that we can put those into a nice graphing calculator into the internet, but I prefer you to do them algebraically so that we get that practice of solving things using those variables. We're going to use the substitution and the elimination methods, and I'm going to ask you to check your work so then you can pull in those graphing software and be able to check your work on that, but we do want to be able to show that work algebraically in order to solve these equations. So let's go ahead and look at an example. We have x squared plus y squared equals 10, and we have y equals 2x minus 5. So the first thing I'd like for you to do is go ahead and think about what kind of equations these are. What are these equations? If I have x squared plus y squared equals 10, I notice that both of my x and my y terms have a squared in them, and I also notice that the leading coefficient for each of the x and the y is going to be 1. So I know that this is going to be a circle. So if I were to draw a circle, I also know that the radius is going to be 10, so it's going to go somewhere maybe in here where it comes out to be the square root of 10, or just over 3 in each direction. I also have y equals 2x minus 5. So if I think about that equation, that's a linear function. And if I were to graph that, I know that graph is going to come down here just below this point here, and I'm going to have a slope of 2. So it's going to maybe come up something like this. So if I were to think about this, it looks like I'm going to have 2 points of intersection. Now, my drawing could be off because I don't have this as accurate as I probably should. So what could possibly have happened? This could, maybe, if my slope isn't right or my y-intercept, we could see something maybe like this, where here we had 2 solutions. Notice here I don't have any solutions. Or maybe this circle comes in here and I just skirt. We call this a tangent line in math. This could possibly touch at just one point. So I could have 2 solutions, I could have no solutions, or I could have 1 solution. So we're going to go ahead and do this algebraically and be able to solve and find those solutions. So with this one, we can do elimination or substitution. When we have a variable by itself, recall we like to use the substitution method. So we're going to take that y information and plug it into the y in that first equation. So I know x squared is going to equal, or x squared plus my 2x minus 5, that's my y value, squared is going to equal 10. So I can go ahead and solve then this equation. So I get x squared plus, I'm going to take 2x minus 5 and square that out. If we need to, come off to the side and write 2x minus 5 times 2x minus 5. Multiplying that out, we get 4x squared minus 10x plus 25, or 4x squared minus 20x plus 25. Again, if you need to do that off to the side, go ahead and do that. Take you a little bit of time, but we do need to be able to get that correct. Now we're going to go ahead and combine like terms. And notice I have all x terms now, so I don't have to worry about that y value at this point in time. Now I'm going to go ahead and set it equal to 0. I have a quadratic, so I'm going to set it equal to 0. So I can go ahead and solve for x. So I get 5x squared minus 20x, subtract my 10 over, so I get plus 15 equal to 0. Now I have this quadratic equal to 0. I'm going to use my quadratic methods in order to solve a quadratic. I can go ahead and factor out a 5. So I get x squared minus 4x plus 3 equal to 0. And I can go ahead and factor that quadratic. So I get x minus 3 and x minus 1. So I end up with x equals 1 and 3. And notice that kind of goes along with what I had over here, doesn't it? I had this point, these 2 points here, so my first inclination was pretty accurate there. Once I have my x values, I can go ahead and find my y values by substituting that back into one of my two equations. Remember, these are the points of intersection, so it doesn't matter which equation I choose, I'm always going to get a true statement for both equations. So I'm going to pick the easier one. I'm going to take y equals 2x minus 5. I don't really want to mess with those squared terms up there. So I'm going to have y equals, my first one, I'm going to plug in my 1, so I had 2 times 1 minus 5. 2 times 1, that's 2, minus 5 gives me negative 3. So my first point, I'm going to write off to the side here, which is going to be 1, negative 3. Again, that goes along pretty close to what I thought up here. And then my second equation is going to be y equals, I'm going to plug the 3 in for my x, so 2 times 3 minus 5, so that's going to be y equals 1. So I get the point 3, 1. And again, that kind of goes along with what I had first thought that this graph would look like. So those are my two solutions, 1, negative 3, and 3, 1. Looking at our next example here, we have 5x squared plus y squared equals 36, and x squared plus 2y squared equals 36. So first looking at these, I see I have two ellipses. I have one that's going to be parallel to the x-axis and one that's going to be parallel to the y-axis, and they're both centered at the origin. So if I think about that kind of graph, this is going to be a rough graph as well, but notice if I have two graphs, one parallel with the x-axis, one parallel with the y-axis, I can have up to 4 points that I can have as points of intersection. Again, depending on how accurate we are, these graphs could possibly intersect in different ways. So we have 4 here. We could see this. Maybe it comes down here and just touches. Remember that tangent could be tangent down here. So here we'd have 3 solutions. Possibly, again, maybe it doesn't go all the way down. Maybe it kind of comes up here. Now this one wouldn't be centered at the origin, of course, these are that one. But we could see that we have 2 solutions. We could see that we have 1 solution where they're just tangent to each other at one point, and we also could see where we have no solution whatsoever. So we could see something where we'd have no intersection points at all. So how am I going to go ahead and solve this system? Well, notice I don't have one of the variables by itself. I could get a variable by itself. I could go ahead and take this bottom equation, subtract my 2y squared over, and that would allow us to do a substitution here. I could subtract my 5x squared over and allow me to do substitution up there with my y squared. And what I would do is, on this one, would probably do an elimination problem, actually, since my x squareds, my y squareds, and my numbers are all lined up already. I would go ahead and multiply a negative 2 to my top equation. The reason I'm going to multiply a negative 2 to my top equation is so that I get a negative 2y squared. And when I add these two equations together, it will eliminate my y values. So multiply my negative 2 through, I get negative 10y squared minus 2y squared equals a negative 72. That's an x squared. Where did that y come from? So we get x squared plus 2y squared equals a 36. That's just my second equation brought down. Now I'm going to go ahead and add these two equations together. So I'm going to add my x squared terms. So I get negative 9x squared. My y's are going to cancel. Equals negative 72 plus 36 gives me a negative 36. I can go ahead and divide by negative 9. So I get x squared equals 4. Taking the square root of both sides, I get x equals plus or minus 2. If x equals plus or minus 2, I can go ahead and back in, do a substitution. Again, it doesn't matter which equation you use. I'm going to choose the bottom one here just because there's less happening with the x's. but you could by all means use the top one again, because remember, we're looking for a true statement between all of those, between those two equations. So I'm going to plug in my 2 to start with. So I get 2 squared plus 2y squared equals 36. 4 plus 2y squared is going to equal 36. Subtract my 4. So 2y squared is going to equal 32. I'm going to divide by 2, and y squared is going to equal 16. If I take the square root of both sides, y is going to equal plus or minus 4. So when I plugged in a positive 2, I got 2 different answers. So I have a positive 2, I could have 4, or I could have positive 2, negative 4. So there's going to be 2 of my solutions. But wait, there's more, because we can take that negative 2 and plug it in as well. But let's notice what happens when we plug in that negative 2. And some of you are going to say, I don't need to do this problem. I'm done. Because negative 2 squared is what? It is 4 plus 2y squared equals 36. And notice I just did this problem, didn't I? So I know the solutions here are also going to be plus or minus 4. And if you don't like that, if you don't notice that that is the solution up here, or the same solution, you by all means could solve this equation, and you end up with y equals plus or minus 4. So 2 more problems, or 2 more solutions, are going to be negative 2 when we plug in that, and then our plus or minus 4. So negative 2, 4, and negative 2, negative 4. And that's going to be our 2 solutions here. And again, that kind of goes along with my first rendition of what I thought this graph was probably going to look like as I sketched out my possible answers. I have one more problem to play around with. This one's a little different. Excuse me, a little cough this morning. We have xy equals 6, and we have x squared plus y squared equals 12. This equation we have not worked with at this point yet. This is called a rational equation or equation. And the reason that is because if we divide by x or y, then we end up with a rational equation up here. And then we have x squared plus y squared equals 12. That's going to be a circle for us. So what does a rational look like? A rational equation, in the basic of forms, y equals 1 over x, is going to look something in this form. And we will, again, work with rational functions here later on, but that just kind of gives you an idea of what it's going to look like. So if I take that xy equals 6, and I had y equals 6 over x, that's going to look very similar to this as well. So our parent function, we talk about parent functions quite a bit here in Algebra 2 and Pre-Calculus, is 1 over x. So 6 over x is going to look very similar to 1 over x, just our scaling is going to be a little different. And then we have a circle. X squared plus y squared equals 12, again, centered at the origin. And most of our problems are going to be centered at the origin. So what could happen? Well, we could see something like this, where we have no solution. Marker's running dry a little bit. We could see where we have 2 solutions. And we could see where we have 4 solutions. It's a bad looking circle, isn't it? So we could see 4 solutions there. And we just got to figure out what we've got. So how are we going to go ahead and do this? Well, I would do a substitution again. I would go ahead and solve my first equation here for either x or y. I like to solve for y myself. So we're going to take that 6 over x, and we're going to substitute it in to our circle equation. So we have x squared plus 6 over x squared equals 12. We're going to go ahead and square out this term, so we get 6 x squared plus 36 over x squared equals 12. I can go ahead and multiply by a common denominator to eliminate that denominator, so I get x to the 4th plus 36 equals 12x squared. I'm going to go ahead and move my 12x squared to the left side. So we get x to the 4th minus 12x squared plus 36 equal to 0. And we're going to go ahead and factor this. We haven't talked about factoring x to the fourth too much at this point in time. We will spend a little more time again later on. But x to the fourths are going to factor very similar to x squareds. So we're going to multiply our first term in order to get x to the fourth. And we know that we have to have these to be very similar to each other. So x squared times x squared is going to give us x to the fourth. In order to get our last two terms, they have to multiply to give us 36. So I know that's going to be a 6 and a 6. In order to add, to give me that negative 12, they're both going to be negative. So again, that should look very familiar, very similar to us as we did our quadratics. We can go ahead and set each of those parts equal to 0 now. So x squared minus 6 equals 0. And look at that, that's the same thing. So we don't have to worry about writing that second equation because we already have it. So x squared is going to equal 6. Take the square root of both sides, so x is going to equal plus or minus the square root of 6. I can take that information and plug it back in for my y to solve for my y. So I know that y is going to equal 6 divided by the square root of 6, and y is going to equal 6 divided by the negative square root of 6. And again, we haven't talked about rationalizing excuse me, that denominator. We could multiply by radical 6 over radical 6, and that's going to leave us with 6 radical 6 over radical 6 times radical 6 gives me 6, and our 6's will cancel, so we just get a radical 6. So it gives me the point of radical 6, radical 6. When I plug in my negative value into that, I can also go ahead and multiply by radical 6 over radical 6, which gives me 6 radical 6 over negative 6, which gives me a negative radical 6. So that gives me the point negative radical 6 and negative radical 6. So that gives you an idea of what we could see as we solve these systems of conic sections. Remember, I would suggest that we sketch a curve to start with and kind of get an idea of what could happen, and then go ahead and solve it algebraically. And if you want to, go ahead and get an algebraic solution graphing calculator on the internet or on your TI-84 and be able to put these into the graphing calculator. If you have questions, let me know. Good luck and enjoy.